in this video, this will be an introduction to nonlinear algebra. The learning intention of this video is for us to explore linear and nonlinear relationships, and lastly, we're going to be able to sketch graphs of quadratic equations. As stated in the learning intention, one of the main outcomes for us is to be able to identify the differences between linear relationships versus nonlinear. Now, in our previous unit, we've already covered a lot of linear algebra. So we were pretty much looking at linear relationships. And we said that a linear relationship is pretty much when you've got an equation when graphed that yields a straight line. And there are a number of ways for us to identify whether something has a linear relationship. Firstly, one of the ways for us to easily identify whether something has a linear relationship is when the highest exponent, meaning the highest power for a letter, is going to be 1. So as you can see over here for this particular equation, this is a linear equation because the power of y is equal to 1 and the highest power of x is also raised to the power of 1 as well. Secondly, this is the most obvious one, but your graph should yield a straight line. The third dot point says that you will have a constant rate of change, which means that your gradient will be uniform as you pretty much go from left to right of the graph. So for instance, if you were to produce this particular, if you were to graph this particular equation over here, notice over here that your gradient is going to be constant as you move left to right along the actual straight line. So as you can see, if I move 2 units to the right, this will always increase by 1 unit, and this will always be uniform throughout the actual graph itself. And lastly, we could tell something is a linear equation if it can be represented or rearranged in the form of y equals to mx plus c. Okay, so these are the main features for us to identify whether something has a linear relationship. In contrast, a non-linear relationship is defined where you have any equation when graphed which produces a curved line. And if you look at the diagram on the right hand side, this is just a pretty a fun cartoon version of all the different types of graphs that you will encounter if you wish to study maths methods in year 11 and year 12. So you might be seeing parabolas, you might be seeing circles, you might be seeing sine, cos, tan graphs, square root graphs, truncuses, hyperboles, cubics, all the good stuff over there, okay? So what you need to be able to do is identify nonlinear relationships, and the very first one is probably the best one to memorize. So you can easily recognize whether something is a nonlinear if the highest exponent is going to be 2 or a higher value. So that means in this case, if you have an x squared or an x to the power 3, this would indicate that you have an equation that's no longer linear, okay? Secondly, another way for you to identify whether something is going to be nonlinear is if the variable, meaning the letter x in this case, is found in the denominator. So in this example over here, when you've got 1 over x, then you're going to be producing this particular graph over here. And in this case, as you can see, this produces 2 curves. Another way for you to distinguish whether something has a nonlinear relationship is that if you look at its graph, it's going to have a variable slope. So it's not constant as illustrated previously for a linear graph, okay? And lastly, the equation cannot be written in the form of y is equal to mx plus c. I'm just going to go over what this particular point over here means in a bit more detail. So for instance, we're going to be mainly looking at quadratics for this particular unit, and this is what the graph of a quadratic equation would look like. And as you can see by this particular graph over here, if you're going to be comparing the rise over run, notice that for every unit you move to the right, for this case over here, this increases by 1 unit. However, if you're going to be comparing the gradient between these 2 points over here, so if I move 1 unit to the right, in this case, this is now rising up by 3 times. So in this case over here, this is showing you that the gradient is not uniform. It doesn't increase by the exact same rate as you move left to right for that particular graph over there. The reason why we are studying nonlinear relationships is because many real-life world processes and things actually model a curved line in this case. So for instance, projectile motion, which is like the study of like objects that are thrown in the air, they actually follow this particular arc shape of here. So we can actually model that and find its equation. Similarly, we've previously learned about compound interest, which is another example of showing non-linear relationships. In this case, it's showing you exponential growth. So in this case over here, this is a very nice summary of the different types of graphs that we will be encountering in this particular course over here. We've already looked at linear relationships, and the two main types of non-linear relationships that I want you to know about are quadratics, okay, which produces a happy face or an unhappy face graph, or an exponential. But we're not really going to be looking to this in a great level of detail. We're just mainly going to be looking at quadratics, but it's good to know what an exponential graph actually looks like. Now that we've covered the different types of relationships, I want you to please give yourself 1 minute for you to be able to identify whether the following equations is an example of a linear equation or a non-linear equation. Give yourself 1 minute and then we'll compare our answers together. For the very first equation, guys, you should be able to recognize that this is a linear equation since the highest power for each of the variables, so for each of the letters, is 1. Okay, so this is the same thing as saying y to the power 1 and x to the power 1. In the second example over here, this is an example of a nonlinear relationship. More precisely, this is an example of a quadratic since the highest power is not equal to 1. So when you have a power that's not equal to 1, this will clearly indicate that it's going to be a nonlinear. The third example over here, it will be an example of a linear since the highest power is 1. And for the very last example, since the variable x is found in the denominator, then this is going to be an example of a nonlinear equation. What we're going to be looking at now, guys, is we're going to find another way for us to see whether an equation is classified as a linear, quadratic, or an exponential by looking at something referred to as the table of values. To recognize whether an equation is linear, quadratic, or exponential without referring to its graph or equation, what we do is we need to examine the differences in the y values between successive x values. If you guys don't understand what I mean by successive x values, successive just means the next one, so the next consecutive number in this case. So in this case over here, notice that this increases by 1 each time. So these values are referred to as successive x values over here. So my question to you guys is, what do you guys actually notice about the y values between the successive x values for a linear equation? So in this case over here, can you guys see whether there is a pattern line? Could you also describe what is actually happening? So in this particular case over here, guys, you can actually see that as x increases, your y value will actually decrease by the exact same rate every single time. So in this case over here, it's going down by 4. So that's what I mean by a common first difference of -4, because it will always decrease by -4. And for any linear equation or for any linear relationships, it will always increase or decrease by the exact same rate. So in another example shown over here, notice in this case over here that your y values will always increase by +3 for each successive x value. So this is a characteristic of a linear function or for a linear equation. Let's now look at the patterns and the relationships for an exponential equation, okay? So this over here is the table of values that models an exponential relationship. So what I'm going to get you to do is I want you to closely examine what happens to the y values for each successive x value. So if you go on to the next x value essentially. So in this case here, guys, if you guys were able to identify the relationship, you can clearly see that it's repetitively multiplying by 4 in this case. So from 0.25 to 4, you're multiplying that by 4. To get from 1 to 4, you multiply by 4. From 4 to 16, you multiply 4. You get the idea. So that's repeated multiplication. And this is a key characteristics for all exponential relationships, okay? And I'm going to show you using another example. So in this case over here, notice that for between each successive x terms, the y value, there's a common ratio. You're always going to be multiplying it by 5 every single time. Now, for the quadratic relationship, it's a bit hard for you to actually examine it. So I'm going to pretty much be giving you the answer straight away. But if you want to see whether there's a quadratic relationships in a table of values, you're going to see that the first common difference will not be constant, but if you find the second difference, you will see that it will either increase or decrease by the exact same amount, okay? So what do I mean by this? So as you can see over here, if I go from 5 to 3, that indicates to me that this actually decreases by 2. From 3 to 3, that means this indicates no change whatsoever. From 3 to 5, the first difference over here increases by 2, and from 5 to 9, this increases by positive 4. Now, in this case over here, guys, as you can see, the first difference is not constant at all. However, if you actually look at these numbers over here, you can clearly see that there is a pattern. You can clearly see that from here to here, this actually increases by 2, this increases by positive 2, this also increases by positive 2 as well. So this is what I mean by that there's a constant second difference. And I'm going to also use another example for me to illustrate this particular relationship. So notice over here, guys, for the first difference for a quadratic relationship, you can see that it doesn't go up or down by the exact same amount. But however, if you actually look closely, there is a trend for the first differences. You can clearly see that this will increase by 2 each time, and as a result, there is a constant second difference. So just to summarize what we've just covered so far, guys, if you can find that there is a common constant first difference, this indicates that you've got a linear relationship. If the second difference is constant, then you've got a quadratic relationship. And if you can see that there's repeated multiplication, then this is an example of an exponential relationship. So what I want you to do, guys, is I want you to please answer this question over here. Give yourself 3 minutes, and then we'll compare our answers together. So for the very first question, part A, we can clearly say that this is not an example of a linear relationship because it doesn't increase by the exact same rate. So in this case over here, from 1 to 0, that's going down by 1. From 0 to 1, this now increases by 1. From 1 to 4, this increases by positive 3. And 4 to 9, this increases by positive 5. However, if we try to see whether the second difference is constant, then this would indicate that this is going to be an example of quadratic relationship. So let's see if there is a common difference. So in this case, if you're from -1 to +1, this increases by positive 2, this increases by positive 2, this increases by positive 2. Hence, for the part A, this resembles a quadratic relationship. For part B, we can clearly see that it increases by positive 2 each time. So therefore, this is going to be an example of a linear relationship. And for the very last example over here, this is actually multiplying by 2 every single time. So therefore, this is an example of an exponential relationship. This is the last part of today's lesson where we're going to be looking at graphing quadratic equations using a table of values. So I haven't really defined what a quadratic equation is. So I'm going to firstly do that before I actually show you how we actually graph it. So a quadratic is any expression or any equation where the highest exponent, meaning the highest power of the variable, is 2. The graph of a quadratic function is what we refer to as a parabola, okay? So a quadratic is pretty much like the symbolic equation, whereas a parabola is the graph of a quadratic equation, okay? And when you graph this, then it could either have a happy face or an unhappy face shape curve. So in this case over here, you've got a happy face curve over here, and there are many features of a parabola that we're going to be looking at in the next lesson. So as you can see by the image on the right hand side, there's the vertex, which is also referred to as the turning point. There are the y-intercepts, the x-intercepts, as well as the axis of symmetry. Now, in order for us to actually graph or sketch a quadratic equation, we can do this in 2 different ways. We could do this by using a table of values and substituting the x values into the equation to find the corresponding y value. Or alternatively, what you could do is you could algebraically solve for the x-intercepts, the y-intercept, and another key feature which is referred to as the turning point. However, I want you guys to keep in mind that if you are using the very first method, this is the most easiest method because it just relies on substitution. However, you're not actually demonstrating the expected skills of a year 10 student, okay? And as a result of that, most of the questions that you're going to encounter later down this course won't actually ask you to graph it using the first method. Instead, they're going to get you to actually algebraically solve for it by finding the x-intercepts, the y-intercepts, as well as the turning point. Let's now look at a couple of examples of how you can actually sketch a quadratic equation using a table of values. So the first step says you need to substitute the x values to find the corresponding y values. So in this case, substitute -2 wherever you see x into the equation to solve for y. So if you guys were doing this, it would be y is therefore equal to 2 bracket -2 whole squared plus 4, and we therefore need to use our understanding of BODMAS to just pretty much simplify this, okay? So in this case over here, we'll just look at the brackets first. So -2, we therefore square it. So -2 whole squared is equal to positive 4, because two negative numbers multiplied by each other will give you a positive number. In this case, positive 4. And positive 4 times by this 2 over here is equal to positive 8. And positive 8 plus 4 is therefore equal to positive 12. So therefore, this over here is going to be 12. You do the exact same thing where you substitute -1 into the equation to find the y value, and repeat the exact same process until your table of values is completely filled. Once you've actually filled out your table of values, then the way that you're going to actually do this is you need to now plot each of these coordinates on a Cartesian plane. If you guys don't recognize what are the coordinates, these are the coordinates over here. Okay, so therefore you could write this as -212, -16, 0, 4, 1, 6, 2, 12, and therefore plot each of these coordinates on your graph over here. So therefore, if I did this, then this is what this would actually look like. And now the last step simply says to now draw a curve that passes through each of these points. So therefore, if I was to draw a curve, then this is what my graph will look like. But it's really critical that you try to draw your graph very symmetrical, because a parabola is a symmetrical curve. Okay, so please make sure you are drawing this to the best of your abilities, because you will be deducted some marks if your graph looks very ugly essentially. Let's look at another example. So again, we're going to be substituting the x values to find the corresponding y values. So if you substitute -2 in, it would be y is equal to 4 minus -2 whole squared. Y is equal to 4 minus -2 whole squared is equal to positive 4. But it's because there's a takeaway sign here, this is why you've got a subtraction sign here, which therefore equals to 0. Similarly, we are going to be repeating the exact same step by substituting -1 into the equation, 0, 1, and 2. And if you guys have done this successfully, then this is what your table of values should now look like. Now that we've done this, we essentially need to plot each of these coordinates onto our Cartesian plane. So this is what it should look like on the right hand side. And lastly, all we need to do now is now draw a curve that passes through each of these points. Hence, this is going to be the graph or the parabola for this particular equation over here. What I'm going to get you to do now, guys, is pretty much answer these 4 questions over here, just so that you get extra revision and practice. So answer this question, this question, this question, as well as this question. This is pretty much the end of today's video. Hopefully you're able to meet the success criteria. I'll see you guys again in the next video. Bye.